Hello out there. I'd like to share with you something that I recently discovered in terms of how to learn mathematics. Something that can be applied to all of our studies. I've spent years as a student trying to perfect these techniques and trying to find out techniques from other students who probably didn't want to share them with me because of the competitiveness of our studies in college. But today I'd like to share with you something that I've been working on a long time, which all culminated in a work just a few weeks ago. Something that I've been trying out with my students in several of the major school districts in the Dutchess County area. And so, hopefully you can share my excitement after I finish making this presentation to you. The paradigm to loving math. Learn by example, how a mathematician can learn, study, understand, and discover. It was this discover part that really got me excited, where I discovered something new in mathematics. Not that something was brand new, something had been discovered before, but I was amazed at how this process led me to that. It all began with the 3x3 magic square. Something that all of you are familiar with in school, but basically you learned how to solve it, and that was about it. But when I began starting to work with students, I began to notice patterns. I noticed that the even numbers were in corners. I noticed that the 5 was in the center. And I noticed that I could get more than one solution. And of course, I'd been taught that the secret to this was getting all of the triplets, including the diagonals, to add up to 15. But I never asked the questions why this worked. And that is where I now discovered the whole process for studying. It also allowed me to discover. I discovered I was going along the same path as a mathematician would be. And I thought this would be exciting to share with you. So, let's answer the first question. We notice that if we add up all of the numbers, which go from 1 to 9, that they will add up to 45. And then we look and say, well, you know, there are 3 columns. And since all of these triplets add up to the same, and I'm using all the numbers, then I may take 1/3. It was a logic that even a smart second grader could see, with an intuitive knowledge of fractions or divisions. So, this was answer to the first question, but we're going to discover this is important to help us answering other questions. Okay, so we start off with something simple, a little picture. We notice that if we look at the triplets, that in the corner we can have 3 triplets. One horizontal, one vertical, and another on a diagonal. In the middle edge, we can only have horizontal and vertical. But in the center, we can get triplets going in 4 different directions. So, let's see where we go from here. Well, first I want to start off with making all the possible doublets. And what you can see is that I have used first 1, and then all the numbers from 1 to 9, getting up to 9 in the first column, and all the numbers from 1 to 9. That was all the doublets I could think of, 81 of them. However, I'm really interested in triplets, not doublets. So, I took advantage of that first rule that all the triplets must add up to 15. So I didn't get any more triplets and doubles, but now I got a whole series to look at. And now I'm trying to see if I can find something interesting in this. Well, what I begin to notice is I'm only allowed to use numbers between 1 and 9, and yet I'm picking up 10s, 11s, 12s, and 13s, which are not available. And then I also notice in the first one with the 1s, that 177. Well, not doubles. So when I did that, I'm left with 4 triplets. But then I noticed the 168 and the 186 were the same, just one was a commutative other. And similarly, the same with 159 and 195. So when I was finished with all the ones, there were only 2 acceptable triplets. Doing the same thing with the 2s, I found there were 3 acceptable triplets. But with the 5, I found there were 4 separate triplets, which now made me realize why 5 had to be in the center, because it was the only number of these triplets, if I had looked at all the rest, that had 4 triplets going through it. Okay, now I show you the rest of it, and after doing this, I discover I can see that the even numbers all have 3 triplets, not just the 2, but the 2, 4, 6, and 8. And the odd numbers had 2. This now answered another question, why the even numbers had to be in the corners. And of course, we already discussed why the 5 had been in the middle. So it turns out that this work that I just did is going to be thrown all away. And the next time I would do the problem, I wouldn't do it. But I got some insight from this. And that insight gave me an easier way of doing the same thing. After I had removed those triplets out of those 81 triplets, I was left with 24. And if I looked through those, I would be left with 8 triplets. And if you notice something interesting, when we go through the 1, if I find the first increasing number that can give me a legitimate thing, which is the 159, so 1, 2 would have given me a 12. But once I did this, I can go down 1, or up 1, and down 1. Do the same thing with the 2. Down 1, up 1, down 1, up 1, down 1. But when I went beyond this, I would get 2, 7, 6. And I'd see the numbers would change order. So I realized that once I saw the changing order, I didn't have to go any further. This occurred also with the 1, but I got 177 before I got 186. And doing the same thing with the 3. We are always increasing, because if I'd gone 3, 2, I would have picked that up in the 2 somewhere else. Okay, so I start off with 3, 4, get 8, 3, 5, get 7, and the next one will give me 3, 6, 6. And then find that 3, 7, 6. So I know I don't have to go any further. And 4, 5, 6, that's it. And now anything else, like if I went to 5, 6, 4, I'm starting to decrease. So with this particular process, I found an easy way to get the 8 triplets. But I didn't understand this until I started studying those 81 triplets to see what the pattern was. So the pattern helped me get in the right direction. Okay, now, after we've done this, we can go through, write down the number, and we see 2 for 1, 3 for 2, 2 for 3, and 4 we find 1, 2, 3, change that the 4 fit in. The 5, 1, 2, 3. So that's all the work I had to do. I showed you how to find the change, and I showed you how to do this. Fraction of the time that it took me to do it otherwise. Now, we also talked about the possibility of being more than one solution. Well, we can see that 5 has to be in the corner. Okay? And then the 2 and 8 could be in any one of the corners, but we've chosen to put the 2 there, and we'll rotate ourselves around to get the other 2s. Okay, now, which would then give us 4 different corners. But now we found we could put the 2, 9, 4 there, which would leave us with the third triplet for the 2, 2, 7, 6. The 4 and the 6 had to be in the corner, making use of the even number rule we discovered. But we could also, instead of putting 2, 9, 4, we could put 2, 7, 6 and do 2, 9, 4 this way. So there were only 2 possible solutions when we had 2 in the corner. And since we can put 2 into 4 different corners, that gives us 8 solutions. So I've now answered all the questions I asked. But maybe there's some more questions to ask. Let's take a look. Okay, so one thing we did is that could be a slow way to generate the magic squares. So what we do is we can see that we can just rotate them one at a time. We could also reflect and then rotate. That's another way of getting the 8. But the problem is, suppose we, instead of flipping it this way, on the vertical, we flipped it on the horizontal. Well, what we would find then, that if we did 2 rotations, behold, we get that. When we do a vertical and a horizontal flip, we get the same thing. So that extra flip would just have given us duplicate solutions. And so now we find that at first we would have thought we had 12 solutions. Now we find that we really do have 8. And where this becomes important is we would now develop a math called group theory, which would show us how to analyze these rotations and flips and help us in our count. So taking this simple little problem, which only required us to be able to add 1 and 1 and subtract it from 15 to get 13, and then just using our counting approach, counting up from 1, 2, 3, 4, 5, and then counting down, 13, 12, 11. So with hardly any math skill, by just looking for patterns, we were able to give answers to this problem. It's something interesting you would try with your teachers, because I was never taught this. It took me time to figure this out after showing this to hundreds and hundreds of students on a special magic square board that I have. Well, let's try changing the rules. Never thought of that. And let's not require that the sums have to be along the diagonals. They just have to be along the horizontal and vertical. Well, once we do that, we see that now, no matter what position we pick on the magic square, we only try 2 chains. This is now going to be an interesting problem, is what happens to those 4 5s and those 3 even numbers. Okay, so we start with putting 1 in the corner, and we have a chain that could go 1 5 9, or 1 6 8, or we could put 1 6 8 up on the top, and we could come 1 5 down the side. Well, once we do that, we see that we have now 2 solutions from each of those things. Let's see how many variations we can get in before. Well, since the 9 was an odd number, we only have one other chain. We've already used that, the 9 2 4 chain. But we could put 9 2 4 or 9 4 2. But if we put 9 4 2, we find that we need we get 5s in the middle. So we're not going to use the 6 5 4 chain or the 2 5 8 chain, which is where now those chains have disappeared, leaving us with 6 chains. And so now, from this point here, we have this. But now we get into another area of mathematics called permutations. There are 6 ways that we can raise 159. That can be written as 3 factorial since we have 3 numbers. And I've shown you the 6 ways we could figure it without us having to understand factorials. So the 159 has 6 permutations. The 168 has 6 permutations. Therefore, we would have 32 solutions. But because we have 2 starts, that gives us 72 solutions. Still something we can prove using group theory. Now, we'd like to feel comfortable about the answer. We had started off with 1 in the corner. Well, what about if we put an even number in the corner like it was before? So when we get the even number in the corner, is, as I mentioned, there are 6 different ways that we can permute that. So one of these permutations could have 9 starting first, then 5, and then 1. And now we have 2 here. And then we do the permutation this way. And so we interchange these 2, and the 2 now is first, and now we have the 2 in the corner. Now we can now force the 2 into any corner, so we're not going to be doing rotation. Everything is going to be done by translation. And again, the group theory would show us how a translation, in this particular case, is equivalent to a rotation. Well, hopefully you can share my excitement. But it's going to take time. And what you may have to do is just watch this video over a couple times. My plan is, since I'm moving along with this rather quickly, is to put the pages on a PDF file and make that available on my workspace. So if you want to contact us, we're at 1054 Freedom Spring Road, which is Poughkeepsie, New York 12603. The organization is called Math and Physics Exploration. Our phone number is 452-4862, area code 845. My email address is immiller1@juno.com, and one of my websites is itmeansmath.com. Another one is mathphysicsexplore.org, but right now I would like you to focus on this particular one. Thank you again for watching, and happy studying.